So the epidemic spread model that we have discussed so far, SIR, SIS, SIRS, all these models, so they assume that the graph is completely connected. I mean, all the nodes are connected to, I mean, each node is connected to the remaining nodes in the graph, right? It's a completely connected graph. And why we assume that? Because this is the simple, representation of a population. We assume that all the, all the citizens in a population, they are friends of each other, and that's the simple way, and that's the worst possibility. I mean, whatever prediction you make, you are making the prediction on the worst possible case, right? Let's assume that you know the network structure, and you also know that each node is infecting another node with certain probability. Okay, let's say this is the graph, okay, and all these nodes are there. So this node, for example, infects this node with probability 0.3, this node infects this node with probability 0.4, and so on and so forth. And it is not the case that the sum of all the probabilities of the outgoing edges for a particular node would be 1. No. So with certain probability, a node will infect another person. That node will infect another node with a different probability. Okay. If this is the setting, then how do we predict the cascade growth, right? So we will discuss a new model called IC model, or independent cascade model. Okay. So here the idea is that, as I mentioned, the spread of infection with uniform probability between any node pair may not be realistic. In SIS model, we assume that the graph is completely connected, and this guy is infecting this guy with same probability as infecting this guy. Similarly, this guy is also infecting this guy with same probability. So all the edges, if you think of edges and the associated probabilities, they are all same. The infection rate is same. So the infection rate is beta, right? But in real world case, as I mentioned, transmission of disease may be more probable between certain pair of nodes than the other pair of nodes, right? So if this is the case, then how do we deal with this? Now let's first understand how this model works, right? So say this guy is infected, right? And you look at this pair first, okay? And with probability 0.4, you infect this guy, right? Then you look at this node, this pair. With probability 0.3, you infect this node, okay? And why this is called independent cascade? Because this infection is independent of this infection, right? So if you look at a cascade through this path, this cascade is independent of this cascade, for example, right? So now let's look at the problems here. So independent cascade model is simple, but if you think of all these probabilities associated with edges, all these probabilities are different, and how do we compute it? So you can think of these probabilities as different parameters that you can derive from the data set. So you actually need to estimate a lot of parameters, right, from the data. So what's the simple solution? The simple solution is that you assume all the edges with same probability. So all the edges have same probability of infecting others. So if this is the assumption, then it is same as SIR model. Then there is no difference. The only difference is that it is not a clique, whereas in SIR model we assume that the structure is clique. Otherwise, the remaining part would be same, right? If all these numbers are same, then it's basically a single parameter beta, right? So how do we make this thing little better? Okay, so we define something called exposure and adoption. Okay, so exposure is basically a node's neighbor exposes exposes the node to the contagion, to the virus, right? So exposure is basically event of a node being exposed to a contagious incident, right? And adoption is the event of the node acting on the contagious incident, right? So adoption is that the node actually acts as a contagion. It has already got infected, and exposed is basically, that you are exposed but you are not infected so far, right? So what you do, we draw something called exposure curve. Okay, exposure curve, right? What is exposure curve? So in the exposure curve, we will basically look at the change of the change of adoption, right? The rate of change of adoption with the number of friends who have already adopted, right? So the rate of change of infection with the number of infectious neighbors. Okay. For example, if you look at this curve, right, x-axis is the number of adoptions, number of infections, basically number of friends who are already infected, and y-axis is the probability that that particular node will be infected. Say this is 0.2. It means that if 20% of my neighbors are infected, what is the probability that I will also be infected? I will adopt it, right? So if you look at the decision based model that we discussed earlier and these probabilistic models, for the decision based model you will see this kind of exposure curve, is this kind of S structure curve, which is quite expected because we know that in the decision based process model there is something called social pressure. With 40% or 50% infections of my neighbors, I will be infected, right? When majority of my neighbors have adopted something, I will adopt it. So you see that a certain peak is here, right, around 0.3, 0.4. Whereas in case of probabilistic model, it basically increases like this, right? So it means that there is no concept of social pressure. It all depends on the probability p, whatever beta, the infection probability, right? It gradually increases. If you look at this exposure curve in other cases, for example, if you look at, you can think of different types of exposure curves. One type would be like this, monotonically increasing, then decreasing, right? These are basically cases where, say, you are infected, you have adopted a particular music, right? So you have suddenly started listening to a music, and then you do not feel that attractive, and then you do not feel that music that attractive, and then you gradually leave. Okay. Another type of exposure curve could be this one, gradual increase over time, and other type of cases would be peak at the beginning and then a decrease like this. So it means that as soon as the product comes, right, you immediately buy it irrespective of what your neighbors are doing. Say for example, you are fond of Apple, right? So as soon as any Apple product comes, right, comes to the market, you immediately buy it irrespective of what your neighbors will think about it or not, and then gradually the interest decays with the increase of the number of exposed, number of adopted neighbors, right, or whatever, exposed or adopted neighbors. Okay, now let's look at some sort of viral marketing, referral based marketing. Okay, say there are 3 persons, right? If this person refers a particular product to this guy, this guy will get $5, this guy will also get $5, right? If this guy refers the product to this guy, right, he will get $5, the other guy will also get $5. So this is also kind of a viral marketing, a cascade, but this is more of a referral kind of cascade where there is an incentive associated with every purchase or every recommendation. Okay, so there was this experiment where around 16 million such recommendations were collected, and around 4 million people were there, around 500K products were considered, right? And if you look at this exposure curve, right, number of purchasing versus number of incoming recommendation. So number of incoming recommendation is basically number of neighbors who have already adopted it, right? This is also exposure curve. So you see that say in case of books or DVD, music, videos, the patterns is more or less same. In fact, you see that in certain cases, so always there is a peak at the beginning, right? They are essentially fans of these movies or whatever, books and DVDs, so they would immediately buy it. And with the increase of recommendation, it will almost remain same, right? There is no such increase. In fact, some cases it will decrease, right? And if you look at the probability, very less, 0.04, 0.606 and so on and so forth. So these numbers are very less. Okay, it basically indicates that this referral business doesn't help much in most of the cases. Okay, particularly for the data set that this experiment for this experiment was collected. Okay, similarly there was another experiment where people looked at this live journal social media similar to Facebook, where say there is a group, there is a fan club and nodes are there. Okay, they are their friends. So these rectangular users, they are already part of the club, right? And these circular users, they are not part of the curve, this group. So what is the probability that these guys will also be a part of the community group, right? And it depends on the number of recommendations. And here the recommendations are basically proportional to the number of users number of neighbors who are already part of this social group, right? So if you plot the exposure curve for this one, you will also see the same pattern. X-axis is the number of recommendations, number of neighbors who are already part of the group, and Y-axis is the probability of joining that particular group. You will see that this kind of curve exists, right? Some sort of diminishing return kind of initially increased, and then after a certain point it will remain constant. Okay, so this was quite interesting. Now if you look at this one, so this is again same sort of experiment on a Twitter data set, right? And this was done by Daniel Romero, one of my good friends from University of Michigan. And this was published in 2011. Okay, and in this paper they collected Twitter dataset and they looked at number of exposures and number of adoptions. Exposures basically seeing retweets of a particular tweet by different users, adoption retweeting that particular tweet after seeing the other retweets, right? If you look at this parameter here, so K is the exposure and P is the probability, right? Probability of adopting it. K is if you look at it here, right? So the curve increases, the value increases and then decreases after a certain point. Okay. So now they tried to understand the important aspect, different important aspects of this curve. Okay, right? And they actually defined two quantities. One is called the persistence of a cascade. This is a cascade behavior. The persistence of a cascade and the stickiness of a cascade. What is the persistence? Persistence is essentially the area under this curve, right? And it is basically the ratio of the total area, okay, the total area, and remember the total area is considered based on the maximum peak, okay. So based on the maximum peak, you draw a square, right? You get square or rectangle, whatever, you get the area and you also get the area under this curve, okay. So the persistence is the ratio of the value which indicates the area under the curve and the total area. So if the ratio is high, it means that the curve would look like this. It is persistent. It is not, and if the ratio is low, it basically means that something like this, right? After a certain point or whatever, after a certain point it will decrease, right? And that is the persistence, right? Higher the persistence, higher the chance that the event will persist forever, right? Stickiness is another metric which captures the maximum peak, the maximum height of the curve, and in this case the maximum height, as you see here, is this one, right? It basically indicates that the probability of usage as the maximum effective exposure, right? When you have maximum exposure, what is the probability of that exposure? What is the probability of that usage, right? So they plotted the values of persistence and exposure for different events, for different Twitter events, for different events which are whatever events or topics which are there on Twitter, right? So now these are events: political, idioms, music, technology, movies, sports, games, and celebrity. So you divide tweets into these different buckets, okay? And y-axis is basically persistence, okay? So let's look at one event, say political, okay? So they also define something called the null model. So in null model, you basically randomly choose a subset of hashtags irrespective of the topic, right? And then you measure the persistence. That would give you the random model or null model. And whenever you compare any statistical test, measure any statistical test, you always do this with respect to a null model, right? So, and this null model value, the persistence value for the null model is same across all the events. So you see this number, these dots are the persistent values of the null model, okay? And this bar graph or the error bar, right? This indicates the standard deviation, because you have to do this null model experiment multiple times because it's a random process, right? You get a standard deviation, and this is basically the mean, okay? Now for political event, the persistence is quite high compared to the null model. For idioms, persistence is quite low. For music, persistence is quite low. For movie also, persistence is quite low. Sports, persistence is high. What does it mean? It means topics like music, movie, right? So these things generally get viral immediately after release. Therefore, you see a peak like this, and then after a certain point, it will deteriorate. The popularity will deteriorate, right? Cascade size deteriorate. So therefore, you see that the total area, right, if you look at the area under the curve and the total area, the ratio would be less, right, you see here. Whereas topics like politics, right, sports, so politics and sports, these are topics which always, you know, last forever, run forever, right. Therefore you see the persistent values are quite high. Okay. Similarly, if you, it is not drawn here in this particular slide, but similarly if you look at the stickiness, right, you will see that the same plot where y-axis would be stickiness and x-axis would be different events. You will see for topics like technology, right, technology, movie, right, sports, stickiness is quite low, stickiness is quite low, okay. But for movie you see persistence is also quite low. For sports persistence is high but stickiness is low. What does it mean? For it means that this exposure curve would possibly behave like this, okay, behave like this. And cases like music, right, celebrity, the stickiness value would be quite high, okay. So if you want to know more about this one, you can either refer to the textbook that I mentioned the beginning, or you can look at the original paper, right, where this was published. All right, let's proceed. So this kind of exposure curve, right, you would see, in fact you would also look at the expected number of the expected time when a particular node gets infected or gets or adopts a particular product or particular ideology, and that you can plot with respect to the number of exposures and so on, exposed neighbors and so on, right. So what task that you can basically model in case of cascade prediction, you can think of it as a classification problem. You can say that, okay, right, given time t, you have a cascade depth of say L, right, with time 2t, right, whether the length, this L would be 2L or 3L or not, right. You can think of it as a classification problem, that given that at t you have the length L, length of the cascade L, at 2t whether it would be 2L or more than 2L or not, right. It's a classification problem. It can be 2L or 3L or whatever. You can basically run different classifiers, right. Or you can think of it as a regression problem. You can say that, okay, at t you have a cascade length of L, right. At 2t or whatever, at t plus delta t, what would be the cascade length? Okay, that would be a regression problem, right. So you can predict the cascade length, and you can also predict the growth, the velocity of the cascade, right. Say you see that within a delta t time, what's the cascade growth, and can we predict the cascade growth over time? So this is basically velocity, okay. You can predict velocity, you can predict the length of the cascade, you can also predict the shape of the cascade, meaning if you think of a tree-like structure, right. So what would be the properties of the tree, what would be the properties of the cascade tree after t plus delta t time period? At time t you have a tree, you have this kind of tree. After t plus delta t, this tree will grow, right. So it would be very difficult to predict the actual tree, but you may be able to predict different properties of the tree. For example, the depth, right, the breadth or number of branches and so on and so forth. And from the property, from this predicted property values of the tree, you can think of the shape of the tree, okay. So this brings us to the end of this chapter. So what we have learned so far, a quick recap, we have basically learned two different types of models, decision based models and probabilistic models. In decision based models, we have seen different cases where right, where you basically model it in terms of the social pressure, right. Then in the probabilistic model, we basically look at epidemic spreading model. So node will infect another node with certain probability, right, and this is different from the decision based model. Decision based model is mostly useful for say understanding how products are being adapted, right, how strategies are being adapted, whereas probabilistic models are useful for contagion spreading, epidemic spreading, right. We have seen models like SIR, SIS, ACIZ and so on, right. We have also discussed independent cascade model and applications of these models in different real world scenario on social network, such as rumor prediction, rumor propagation prediction, and then also understanding exposure curve for different topics, different events. Okay, so hope you enjoyed this particular chapter. This was one of the applications related chapter that we wanted to discuss. In the next chapter, we will start discussing on anomaly detection, graph outlier detection, right. We'll see another application of graph, right, for social network analysis. Thank you.